Welcome back to our discussion on quantum mechanics. Now, before we dive in, I just want to remind you that we are not trying to learn formal quantum mechanics in this unit. The goal here is just to get comfortable with a few key concepts that will help us understand semiconductors. So the topic today is waves in crystals, specifically semiconducting crystals, and we'll begin with the wave equation. This is the wave equation for a constant potential energy U0. And we've seen earlier that when the energy is greater than the potential energy, we can rearrange this equation into a form that has solutions that provide wave solutions. The solution to this equation is a constant times e to the plus or minus ikx. The time-dependent part, we would add the time dependence to it, and we end up describing a traveling wave in the positive or negative x direction. So we get wave solutions. The relation between energy and K is energy is potential energy plus kinetic energy, h bar squared k squared over 2m. We can also associate a momentum with this wave, and we've seen that the momentum of this wave is h bar times its wave vector k. We can also make wave packets that localize the wave and describe particles, and when we do that, the velocity of that wave packet, which we think of as the velocity of the particle, is h bar k divided by m. That's just momentum divided by mass, just what we would expect the velocity to be. Now, when we're treating atoms, like this hydrogen atom, we have a more complicated potential. In this case, the potential energy is given by the Coulomb potential. The solutions to this wave equation give us the energy levels and the sp-d orbitals that we talked about earlier. They lead to the quantized energy levels that we've seen earlier for the hydrogen atom. Now, when we get to a crystal, the potential becomes a little bit complicated. So here's the end of the crystal, and here's the vacuum where the energy is 0. Inside the crystal, the energy is negative. It's holding everything together. Associated with each atom, there's a potential due to all of the positive charges on the protons and the negative charges due to the core electrons. That could be a very complicated potential. But it does have one simplifying feature, and that is that this crystal potential has the periodicity of the lattice spacing. So it may be a complicated form, but it's periodic in the lattice spacing A. Well, to understand how electrons behave in semiconductors, we need to solve this more complicated wave equation with that more complicated crystal potential, understanding that it is periodic. Well, it turns out that the solutions to this equation have been studied in detail by physicists and mathematicians, and the solutions can be shown to have this form. The solution to this equation with a periodic potential is a periodic component times a traveling wave that we've seen earlier. The periodic component, we call the block function, has the periodicity of the lattice. So the solutions may be complicated, but they have this form, a periodic part times a plane wave. Okay. The wave functions then are periodic in space. It turns out that they're also periodic in K space or reciprocal space. The energy versus momentum relation is an important relation for electrons in semiconductors. We've seen that for free electrons, the energy is p squared over 2m. It's just potential energy plus h bar k is momentum, so this is p squared over 2m. M is the mass of the electron, the rest mass of electrons. If we solve the wave equation for this crystal potential, we find solutions that tend to look something like this. They have a minima. The curvature might be a little bit different. The difference in curvature means that there's a difference in the mass of the particle. This is where the effective mass comes from. But you can see also that these solutions are periodic in K. They repeat themselves in K space. There is a region over which we need to solve that equation. In this simple one-dimensional example, that region goes from minus pi over A to plus pi over A. That region is called the Brillouin zone. And we can reproduce the entire EK relation simply by translating that to other values of K. So since the solution is periodic, we only need to consider the solution within this Brillouin zone, this specific region of K-space. In three-dimensional crystals, this Brillouin zone can assume complicated shapes, but the basic idea is that the solutions repeat themselves in reciprocal space. So we've talked about conduction bands and valence bands. The valence bands are mostly filled. The conduction bands are mostly empty. We've also talked about the energy versus K, or energy versus momentum relation. The conduction band will have a relation that tends to look like this. There's a minima somewhere, and the relation looks like a parabola near the minima. The valence band is flipped upside down. It has a maxima somewhere, and the maxima looks like a parabola around that region. So these solutions come out of solving the wave equation with this complicated crystal potential. I'm showing it here for the Brillouin zone, that part of K-space that is unique and that we can replicate the solution to other values of K just periodically to get the entire solution. Okay, now there is a quantity that becomes very important for electrons in semiconductors, and that's called the crystal momentum. So here's our wave equation with its crystal potential. Here's the form of the solutions. They're block waves. They're unique within a Brillouin zone. Now the momentum of the electron in the crystal is not h bar k, because the electron is being acted on by all of these forces due to the electrostatic forces of the core electrons and the protons in the crystal lattice and everything. But it turns out that there is a quantity called crystal momentum, which behaves much like momentum. For example, we understand from freshman physics that momentum is conserved. It turns out crystal momentum is conserved. So when we talk about momentum for electrons in semiconductors, we're talking about this quantity called crystal momentum, which behaves and satisfies relations that are very similar, almost exactly the same, as relations for free particles in space. So not momentum, but crystal momentum. So the key quantity then that we get from this calculation is the relation between energy and wave vector k. This is what we refer to as the band structure of the semiconductor, sometimes also called the dispersion. Any wave has a dispersion. The energy is equal to h bar times omega, so there is a frequency associated with the time dependence as well. All right, so these are some basics of band structure. We solve the Schrodinger equation with the crystal potential. Here's the valence band. Here's the conduction band. There are other bands higher in energy, and there are other bands lower in energy, but by and large, we don't need to concern ourselves with those other bands. Most of the electrons in the conduction band will be near the bottom of the conduction band. Most of the holes in the valence band will be near the top of the valence band. We describe electrons with wave packets. There's some uncertainty associated. We can make a wave packet, but there will be some uncertainty in the precise location of the particle and in the precise momentum of the particle. If we're describing a particle here with a wave packet centered about k is equal to k naught, those uncertainty relations apply there. If we are interested in the velocity at which that electron is moving, we find it's the group velocity of the wave packet. It's 1 over h bar times the slope of E versus k. So these are some basics that we'll use over and over again. Now, in simple cases, and this will be the case that we will use for the remainder of the course, we can assume that these bands have a very simple structure. That is, near the minima, the conduction band looks like a parabola. And since we're only concerned with near the minima, because that's where all of the electrons are, we can approximate the E versus K relation by a simple parabola, as long as we use the correct curvature of that parabola, or the correct effective mass. Okay. So if we use that, we can then take that effective mass, we can take the slope of the E of k, and we get velocity as momentum, crystal momentum now, divided by mass. Same thing applies for holes in the valence band. We can treat the valence band as a parabola because we're really only concerned with holes that are near the top of the valence band. So this parabolic band assumption is an assumption that is commonly made and generally works pretty well for semiconductors. So because the states are near the bottom of the conduction band, this parabolic band assumption works pretty well. There are examples where we have to do a little bit better, and sometimes people will make a first-order correction for non-parabolicity. You can see that if we get a little bit away from the minima, that there is some difference between the parabolic approximation and the actual band structure. People actually have described that simply. This is a description that is known as Kane bands. You will sometimes hear it referred to that. And you can see that if you look at this relation at a given K, that it will affect the EK relation, and it will describe this flattening of the EK relation. The non-parabolicity parameter alpha is a material-dependent parameter that we can obtain from more accurate numerical solutions to the Schrodinger equation. Okay, so that's a little bit about band structure. Band structure, we talk about reciprocal space, K space, 2 pi over wavelength. There's also the real space structure of crystal lattices that we have talked about earlier. These real space structures get very complicated. When we plot the EK relation, we really need to plot it in 3 dimensions. This is a numerical solution to the wave equation in 3 dimensions along various directions. This gamma point here is the origin in K space 0, 0, 0. This X direction is a 1, 0, 0 direction. This L direction is a 1, 1, 1 direction in Miller indice notation. And you can see that the bands have very complicated structures. But if you look carefully, you can see that the lowest conduction band has a parabola out along the 1, 0, 0 direction, not at K equals 0, but somewhere near the edge of the Brillouin zone in a 1, 0, 0 direction. If we look at the valence band, we can see that there are actually 3 valence bands we see here, and they all have a maxima at the gamma point, K equals 0. So the complicated band structure can be calculated numerically, but we are primarily interested in the region with the lowest energies in the conduction band and the highest energies in the valence band. Now, we will also talk from time to time about constant energy surfaces. If we have a parabolic band, we can express the energy as h bar squared k squared over 2m. Or in 3 dimensions, it's kx squared and a ky squared and a kz squared. And if we have a parabolic band, a spherical band, the effective mass, the curvature is the same in all 3 directions. Well, this is the equation of a sphere. So if I put a constant energy here and plot this surface, I'm plotting a sphere. So we will call these spherical energy bands. Okay, now in some materials, and silicon is an example, things get a little more complicated. The curvature in the x direction, the y direction, and the z direction might be different. In fact, this is the equation of an ellipse. So if I plot the constant energy surfaces in silicon, we found from that detailed calculation that the minima occurred in a 1, 0, 0 direction, somewhere out near the edge of the Brillouin zone. The constant energy surfaces then are 6 ellipsoids in 6 different directions. The curvature in the long direction is the longitudinal effective mass. The curvature in the transverse direction is the transverse effective mass. And they can be quite different. The longitudinal effective mass is 0.9 times the electron rest mass. The transverse effective mass is only 0.19. So silicon is an example of a semiconductor that has, first of all, multiple valleys. We say these valleys are degenerate. There are 6 valleys at the same energies. And they're also ellipsoidal energy surfaces, which complicates things a little bit for us. So putting this all together, this is the model band structure that comes out of silicon. It comes from these detailed calculations. The lowest conduction band is out along a 1, 0, 0 direction, and we have 2 different effective masses that describe the curvature in the different directions. There's a higher valley too, but that doesn't come into play in silicon. The valence band, we actually have 3 valence bands. We have a heavy hole that has very little curvature. We have a light hole that has a much larger curvature. And then there's something called a split-off band, which is also for holes and can from time to time come into play. So the valence band actually gets a little bit complicated. This is an indirect semiconductor because the minima of the conduction band and the maxima of the valence band are occurring at two different locations in K-space. So we can describe the surfaces with an EK relation that's h bar squared k squared divided by 2m, but we'll have different m's in different directions. We can also describe the valence band as a parabolic band, but we have different effective masses for the three different bands. All right, now if we take a different semiconductor material, we'll get a different band structure. So one of the things we need to understand when we deal with any semiconductor material is what is its band structure and how can we simplify it so that we can do calculations analytically. In gallium arsenide, we have a minima of the conduction band that occurs at K equals 0. It has a very high curvature, which means light effective mass. We have valence bands that are similar to the valence bands in silicon. If you look out along the 100 direction, you'll see that there is a conduction band that is a little bit higher in energy. It's close enough in energy to the minima of the first band that it sometimes becomes important, and we need to then worry about it because it can affect the properties of devices. There's yet another conduction band minima if we look in the 111 direction. And that minima also can come into play in higher electric fields. The simplest description of gallium arsenide would be a parabolic band at K equals 0 and a parabolic band that accounts for these bands, these valence bands at K equals 0. Gallium arsenide is a direct gap semiconductor because the minima of the conduction band and the maximum of the valence band occur both at K equals 0. Now, quite complicated band structures can occur for different materials. Complicated in some cases, simple in some cases, but sometimes much different from what we've seen for the parabolic band case. For example, in graphene, the band structure looks much different. Graphene has these conical surfaces. This is the conduction band. This is the valence band. There is no band gap for graphene. It is what we call a semi-metal. Its EK relation is plus or minus h bar, a velocity we call the Fermi velocity times the magnitude of the K vector. So it's not a complicated EK relation, but it's much different from the parabolic relation. We can compute the group velocity of an electron at some K point simply by taking the slope. If you take the slope of this, you'll find the velocity is constant wherever we are. Doesn't depend on the momentum. The velocity is always about 10 to the 8 centimeters per second. Now, this gets a little complicated. If you try to ask what is the effective mass, well, the definition of the effective mass is that it's proportional to 1 over the curvature of the band. There is no curvature of the band, so you might say that the effective mass is infinite. Oh, right. So we would not use effective mass concepts for a material like graphene. We would need to deal directly with the EK relation. In this course, we'll stick to parabolic band semiconductors, but I just want to alert you to the fact that you may encounter materials where the bands have a much different shape, and then you have to deal with them differently. So just to summarize the basics of band structure, electrons in a solid behave as both particles and waves. That's what quantum mechanics tell us. The electron waves in a semiconducting crystal are described by this band structure, energy versus wave vector K. Now, because the crystal is periodic, this dispersion, this E of K relation, is periodic in K. And the periodic part of that occurs within a region of K space we call a Brillouin zone. Since electrons and holes are near the band minima, we can usually, for common semiconductors, treat the bands as parabolic because the band structure is parabolic near a minima or near a maxima. We can then treat electrons and holes as semi-classical particles with the quantum mechanics that alters the effective mass included just by using an effective mass, and by treating the crystal momentum as though it were the actual momentum of a particle. So this very complicated situation where electrons are moving within a very complicated potential that varies on the scale of the electron wavelength can be simplified greatly into a very simple relation between energy and momentum, and a very simple way to describe the velocity of this electron as simply momentum divided by mass. So this enormously simplifies our task in computing and understanding the properties of semiconductor devices. We can also describe the force on this particle as derivative of momentum with respect to time, not the actual momentum, but again, the crystal momentum, h bar k. So this is an extremely simple description of electrons in semiconductors that is remarkably successful and that we will use throughout the remainder of the course.